Good morning, everybody, to this, on a short notice, workshop of our cost action, pendant hydropower, sustainable hydropower. Working Group 1 will have this workshop today, so called Colloquium on Flexibility Impact on Hydraulic Machines Aging. I think the topic is very relevant if I see all the discussions around in Europe and also projects coming up in this way. Everybody's searching on, let's say, flexibility, how flexible can machines be, and of course, what does it mean then for the lifetime of the machines? We have quite a good range of presenters today, all young researchers within their PhDs or closely finished or finished PhDs. I'm really happy to have you here. And on behalf of the cost action, I wish all of us here a nice workshop this morning, and also welcome all online participants. I hope you will enjoy this more or less presentations, good presentations, and I hand over to the Working Group 1 leader, Elena Vagnoni from the EPFL. She will moderate today. Thank you.
Thank you very much, Edward. Good morning, everybody. Also from my side, welcome to this colloquium on flexibility impact on hydraulic machine aging. So as Edward said, we will have 5 presentations from all young researchers that anyway are very expert in this field, as their PhD topic or their expertise in the laboratory where we work is actually very active and with excellent results about this research topic. From these perspectives, so we will see both mechanical engineering perspective and electrical engineering perspectives. So I propose to start with the first speaker. I'm very happy to welcome Ludwig on stage. He will present the challenges associated with flexible use of hydraulic turbines and Norwegian perspective. So as you could guess, he comes from Norway, from Trondheim, so from NINA in particular, a research center, but he did his PhD in NTNU in the water power laboratory under the supervision of Professor Ludwig Leonardo Alerci. And he finished recently, last summer, yeah, if I remember well. So I hand it back to you.
Thanks. Okay, thanks for the introduction. As Elena introduced, my name is Ludwig. I'm a postdoctoral researcher at the Norwegian Institute for Nature Research, but just recently finished my PhD under the supervision of Ole Gunnar Dalhaug at the Water Power Laboratory at the Norwegian University of Science and Technology in Trondheim. And I want to present to you a Norwegian perspective on flexibility in hydropower. And I'm really happy to start off because just as a brief background, something that dropped this week is the global energy outlook from the International Energy Agency, which shows that we still see a big increase in wind and solar photovoltaic. So the installed capacity is just on the rise. We see that recently solar photovoltaic even overtook hydropower in terms of installed capacity. And what we see as well is that this trend will continue. So we see that at least what has been pledged by politicians is that a lot of more capacity and energy generation from solar photovoltaic and also from wind energy will occur in the next years. And that means that we have a huge influx of intermittent energy sources. So we need something to stabilize the grid. And that, of course, can be done using hydropower. And that just goes right in the brink. We will see way more flexible use of hydropower in the upcoming years. So just briefly about Norway. If you don't know, Norway is very favorable for hydropower. We have huge elevation differences. We have a lot of precipitation. We have solid rock mass, so it's just very nice conditions for hydropower. And then if we have a look at the numbers, we see that, okay, we have still about 90% of the electricity being generated by hydropower. It used to be even higher, but now wind and solar are pushing the percentage down. Still, it's a large share, and those about 1,800 power plants are just distributed across the entire country. We see a huge number being installed on the west coast, which is even wetter, with annual precipitation reaching up to 2,000 millimeters annually. And there's about 34 gigawatts installed capacity, producing about 137 terawatt hours electricity annually. So this is big. It's the largest hydropower generating country in Europe. And as I said, there's a lot of wind and solar pushing in. Just recently, the Norwegian government announced which offshore wind farms will be put out for being operated, or just planned and then built up and operated. So there's a huge interest in flexibility research. But then again, also we get new power prices, new tax schemes. So it's like really interesting to invest these days. If we look at historic power prices, we see, okay, they were low, very low. They were also very stable, which is okay. You can predict, you can work with this, but you really know, okay, I get this or that power price over the next 10, 20, 30 years. But in the recent years, there's been a huge change to that. We see that power prices are skyrocketing. They are very fluctuating. So that means that also projects that might not have been economically feasible will be economically feasible in the future due to those increase in electricity prices. So this is interesting. A lot of things are changing on the market. And something that is also very interesting about Norway is that there's a lot of high-head Francis turbines installed, from approximately 300 runners that are installed worldwide. More than a third is installed in Norway. And if we look at this table, we see that within this high-head Francis region, so above 300 meters of head, we see that it's also close to a third of the installed capacity that relies on those high-head power plants. So this is something that is really important in Norway. And then again, if we approach a more flexible use, then this will also mean that there is a need for more research, and the research is just usually done at the university. And in Norway, that means it is at the Norwegian University of Science and Technology in Trondheim at the water power laboratory where we're sitting. And through this research and development, we can, of course, increase the knowledge on basics and physics, and also can work together with manufacturers to reduce pressure pulsations, resonance, and cracking. And if I talk about cracking, then there is some history in Norway. And that is of interest, because if we have a look at cracks in turbine runners within the guarantee period, so within 2 years after installation, then we see that that's about 370 turbines that had cracks within this period prior to 2009, so little older numbers, but still we see most of those power plants are actually high-head Francis turbines. So that says something. There's some need to research why those occur. It's also Statkraft, the biggest hydropower operator, that had huge problems. We see that they usually had a third of runners that cracked, and then it suddenly increased to 60%. So It's a huge increase. So Statkraft had a huge interest in this research, and especially the Svartisen power plant, where a crack occurred very close after installation of the runner that pushed off some research. But we see that it's not only Statkraft, it's basically all the big operators that had problems with this, and it's also very big power plants that suffer. So there was and there still is a huge need for research, and this research was then conducted at the water power laboratory. Simple reason for this are, of course, rotor-stator interactions, which increase a lot if we have a look at high-head French turbines with a low specific speed number. So we see that, okay, it's like we know the reason, but we want to know how to prevent it. And this is why the High Francis project came into place at the water power laboratory, where there was research conducted on a model turbine. This is 125.1 model of a turbine installed at the Tokke power plant in Norway, consisting of 15 blades and 15 splitter blades. And this was used to conduct onboard pressure measurements within the blade channel. So 4 pressure sensors installed in the channel to just have a look at what's actually going on within the runner, and then coupling this with flow simulations as well. So what we see is, of course, we have dependency on the fluid load, which could be determined by experiments in the laboratory, and also then proven by simulation. Same for the natural frequency of the runner, which is also something that is important in the rotor-stator interactions. And then the last part that comes into play is hydrodynamic damping, where the structure itself, the flexibility of the structure, will lead to some decrease in the vortex shedding. And combining all this together, we get the actual structural response of the runner. So what we got from this project is a guideline on how to design the runner, just considering all the different parts that will result in stresses on the runner, and then having a more accurate model of the runner before installation. Talking of this dampening, we have a blade cascade at the turbine, at the water power laboratory, where different configurations of hydrofoils could be tested with regard to hydrodynamic damping. And what could be seen is that through the flexibility of the blade, we get, in the end, a linear response between the flow velocity and the damping that takes place. And that is, of course, very interesting. It was both proven by simulation and experimental investigation. And that, of course, can help within the design. But in addition, there was also testing on different trailing edge designs with blunt edges or vortex generators attached to the edge. And that shows that the damping can even be increased using different designs of trailing edge geometries, so that the rotor-stator interactions can be limited in runners. And of course, to investigate wall effects, that cascade was increased to a multi-stage cascade here. This is still linear. It's still ongoing research, and now the most recent research that is conducted at the water power laboratory is a circular cascade, where the blades are just installed in radial fashion, and It's a lot of instrumentation per blade with pressure sensors, strain gauges, and the ability to have downstream measurements as well using PIV. So it's a very extensive test rig that has been put up, and it takes a lot of time conducting all the experiments. So will still take some time until this project is finished. But just, oh, sorry, that was too quick. Can we just start this again? Yes, what we expect is that the dampening and the wall effects in this genre will give us some insights on what actually happens within the turbine, and especially at the outlet. So that's going to be exciting, in my opinion. Something that went on as well was having a look at how we can see failures in operation. And for this, we used the same runner, and we just propagated a shark bite and did measurements. This shows the stages of shark bite that has been tested. So just starting off here and then increasing until the entire bite is taken off, and it even increases. So it's just like a singular blade failure. And using sensors installed close to the guide vanes, which of course then experience different pressures throughout each rotation, we can actually see at which stage we can detect the failure. And of course, if there's the bite developed, so this is stage 9, it's the last stage where we just have a huge part of the blade missing. What we see is that over the full rotation of the runner at the position where the bite is taken off, we just see a huge deviation in the pressure. So yes, this is possible to measure, but it is only possible to see this in stage 8 and stage 9. So huge parts of the blade are already missing. What we're now doing is analyzing the data using artificial intelligence, and it seems as there is the possibility to also detect already stage 4, but this needs to be further investigated. After the High Francis project, Hydroflex came up, was a Horizon 2020 project, and the Hydroflex project was more towards flexibility. So if we have a look at the call, we see that they especially wanted turbine designs that allow start-stop cycles to reach up to 30 times per day. So a hugely flexible turbine. And what we then see is that we have way higher load on the runner and the possibility of way more damage that occurs due to just way more start-stop cycles and low speed part load operations. We also see this from the graph here, where we see that the stresses are way higher, or the highest in load rejections, but then next is start stops and load variations. So flexible use will induce a lot of stresses on the runner over a short number of cycles, which will lead to failure. So what we got was a very nice PhD conducted by Igor Ilyev at the lab, who did a parameter study on designing flexible runners. So he just investigated how the parameters in a turbine design for a Francis runner can be adjusted in a way that a lot of flexibility is possible in the usage. And using this design expression, we designed another laboratory runner that is then more designed for a flexible operation. And on this runner, again, there was a lot of onboard measurements. There was a CFD study conducted to determine where the highest stresses will actually occur in this runner. And then those positions were taken over, and we installed strain gauges at 2 consecutive blades, close to the hub, close to the shroud, and then for reference, one on the hub, and tested those for different configurations of start and stop cycles. And what we see then is that there are huge stresses occurring, especially during startup. So when opening the guide vanes, we see that firstly we have high stresses close to the shroud, and then afterwards the hub side actually experiences high stresses. So this is interesting and can lead to more improved design in the Francis runner with regard to improving the mechanical or the structural integrity on those sites. And now just some additional challenges which I see. There is, of course, environmental impacts from flexible use of turbines. We know hydropeaking, where just the operation of hydropower plants leads to a huge variation in the flow within riverbeds, which then is, of course, very stressful for the aquatic environment, for fish, for aquatic invertebrates, for mussels. So we really need to see how to combine or adjust the flexible use of power plants in a way that the aquatic biota is saved or protected in that sense. One more is total soft gas supersaturation. This is more on my field of expertise, and something that is very recent is a new operating technique that is called synchronous condenser operation, which is a way to operate Francis turbines more flexible by just closing the guide vanes and then introducing air into the turbine space to evacuate all the water from the turbine, and by that reduce friction, so the runner can just spin freely in air. Just really nice from a mechanical side. But then again, if we open up the guide vanes again and then just flush out all that air that we just pushed in, that can then lead to total soft gas supersaturation, which then again is a danger to the aquatic environment. So we really need to have a hand-in-hand research between what's good for mechanical side, so what's good for the turbine, and what's good for the environment on the other side. Something that is also really nice to see is that we can investigate off-design conditions. Here we test vortex generators at the inlet of the runner, and what we see is that we have the efficiency curve of the runner, and we see that, okay, at least from CFD studies, we can push the off-design conditions to better efficiency, which then, of course, is very valuable if we have more operation that is not at the best efficiency point. So that is also something that's ongoing. We'll also conduct experimental experiments on that and then see how that goes and if we can reproduce the results from CFD. But this is also something that is promising. And then all of this goes into Renew Hydro, which is a Center for Environmental Friendly Energy Research. It was just this year approved with a long period from 25 to 33 and will go on under the supervision of NTNU and other research institutes both in Europe and internationally. And it will go on to a more holistic approach on hydropower research. So it will not only have a look at the classic, or what I would say classic hydropower branches, mechanical engineering, civil engineering, and electrical engineering, but it will also include environmental research and some economic studies. So it will be the entire view onto what hydropower makes up. And within the center, I guess there will be a huge focus on flexibility use and the associated challenges. So Norway is just going on financing research in that direction because it's then investing in reaching the environmentally friendly energy generation goals that the state actually proposed. So this is just coming up starting next year, and I guess a lot of PhDs and postdocs will be employed within this center to reach or raise more knowledge on flexible use of hydraulic turbines. And with that, I just have some references and open up for questions, or I guess the questions will come afterwards in a combined session.
First of all, thank you very much.
Well,
Let's give you a close. You kept a perfect timing and with this valuable presentation. So we would have actually time for one question. If there is one now from the audience here or from online. Please.
Thank you for a very nice talk. I had a question about this this plot that you showed us prior to 2009 concerning cracks in Francis turbine depending on the head. And I had a question especially on this kind of cracks or crack that's just, I mean, detected because of regular maintenance or are maybe really failure that appeared on the runner. Which kind of cracks we are talking about here?
I think that this is actually like a long term. So it's like cracks occurring in the 60s, 70s as well that were included. So I think that since it's a large number of runners, this is both total failure and just regular maintenance that includes. I know from a case where there was regular maintenance and the power plant owners they saw that a huge chunk of the blade was missing, some I think 40 centimeters long, and they just didn't detect it from the regular operation.
Okay.
So it is
probably both.
Both,
yeah. Because I see a 25% in maybe cracks and failure, which is a big high number. Okay, thank you. Thank you very much.
Thank you very much. If there are other questions, we will address a discussion and Q&A at the end of the event. I can take care of words. So the next presentation, I would like to invite on stage Giacomo Zanetti. Giacomo is a PhD student from University of Padova under the supervision of Giovanna Cavazzini. He's at the very end of his PhD, and he will discuss this in a few months. He will talk about the challenge for grid stability, pump turbines instability, and their impact on regulation services. The floor is yours.
Okay, so thank you, Elena, for your kind introduction. I'm Giacomo Zanetti, so I'm about to finish my PhD at the University of Padua, and today I will share with you the results of my last 2 years' activity, a part of the results, and specifically we will talk about the influence of the hydrodynamic instability in pump turbines on the regulation services in the grid. So For those of them who are not familiar with this topic, I have reported here a short introduction. So we are all aware that energy storage is mandatory in the grid to support the transition for the clean energy transition, so the development of power production for renewable energy sources. Among all the technologies nowadays available for storing energy, pumped hydro is the most mature and the widespread solution. And the most common mechanical equipment adopted in pumped hydro is represented by reversible pump turbines. However, there is a problem with this specific machine type. Indeed, pump turbines are characterized by an intrinsic unstable nature, which is manifested by pressure, torque, force pulsations while operating both in pump and turbine mode. So here I reported an example of a common characteristic curve of a pump turbine in the high-dimensional speed and discharge factor plan. And unsteadiness, the unsteady behavior of pump turbine manifests itself with a local inflection of the curve in turbine mode in this area called the S-shaped portion, and also in pump mode, so in this area which is called the hump region. And what's the problem? The problem is that when operating close to this area, so like at partial load in turbine mode, the machine could suffer for severe vibration, torque pulsation, also water hammers that could lead to the damage of the machine itself and also to the entire power plant. The same is in the hump region. So the problem is that because of this unsteadiness, the flexibility of pump turbine is affected. In the tail, the switching time from pumping to turbine mode is affected with a long time requirement. And at the same time, especially in turbine mode, the operative range are limited, so the minimum discharge is higher compared to a standard Francis type runner. And the reason behind such unsteadiness has to be found in the design strategy, which tend to favor pumping mode. Now, no, see. Okay, okay. Now, to really appreciate why this unsteadiness is an issue, I reported here the power production from wind energy in Italy. This was the first 10 days of September, so it's a fresh graph from Terna. And as you can see, the power production from, in this case, wind farms, exhibits very high peaks alternated with period without production. And this is a very common feature of power from unpredictable sources. Also, PVs, so photovoltaics, suffer from the same problem. And in this context, it is very important to have a storage system capable of generating and absorbing energy as needed in order to guarantee the grid stability, so the grid frequency, within a very, very short time. So the longer time requirement for the switching mode from pump into entire mode and vice versa of pump turbines is affecting the grid stability by not providing the necessary power input or output in the grid due to the spread of unpredictable energy sources. So when I'm saying that pump turbines are designed preferring pumping mode, actually I'm saying that the geometry of a pump turbine is almost the same as a pump. So here I reported a comparison between a Francis type runner and a pump turbine for the same specific speed. And as you can see, pump turbine runners are characterized by a wider external diameter and smaller height of the channel at the inlet section, so here. While on the contrary, Francis type runners are characterized by a reduced inlet diameter and a larger outlet diameter. And also the blades are quite different, so pump turbines have very long blades in order to better guide the fluids in pumping mode. And yes, we are sure that the unsteadiness is related to this specific geometry, so this condition. However, the correlation between all the geometrical features and the flow unsteadiness nowadays is not completely clear. So the aim of our research was to investigate the unsteadiness in pump turbines by evaluating the flow evolution in the S portion of the characteristic curve, so in the turbine mode instability, in order to better understand the correlations between geometry and turbulent structure, and hopefully in order to propose some new guidelines or new design strategies for improving not the efficiency, because currently we do not have a problem with the efficiency of pump turbines, but to enlarge the operative range and to reduce the switching time requirement. So we performed two different numerical campaigns on two different runners, named as Model A and Model B. The first one is actually the runner coming from the test rig of the Norwegian Hydropower Center, so it's the same test rig as in the previous presentation, but with a different runner. So the same test rig was adapted to feature a reversible pump turbine. Just a few words regarding this hydraulic machine. So it's a standard type pump turbine with the spiral case, guide vanes, and elbow type draft tube. Also the runner, it's quite standard. The only things important to mention is that, as you can see, this is a machine with a very, very low specific speed value. And you can appreciate this in the envelope angle of the blades. Blades are extremely long to better guide the fluid. So a few words regarding the model. So we decided to adopt structured and unstructured meshes. In detail, unstructured for the spiral case featuring the stay vanes because of the relatively complexity of the geometry, while structured meshes were adopted for the other subdomains. We didn't include the front and rear leakage channels in order to reduce the numerical model. Here we have just a few pictures regarding the mesh in the spiral, in the guide vanes and the runner. Regarding the numerical model, so in order to evaluate, to investigate the fluid field in the unstable branch of the characteristic curve, we decided to perform a transient analysis by retracing the machine characteristic curve starting from a partial load safe operating condition up to the turbine break area. So in this case, specifically the zero discharge condition. And to this end, we decided to adopt a varying over time discharge. So during the simulation, the discharge was varied according to this law. And the waterhead was evaluated as consequence, so as difference between total pressure from the inlet and outlet section. So here you can find reported the results of this analysis. So in red, the red line represents the simulated transient condition from partial load to the zero discharge. Here you can see also this part which was used during the validation process. So the model was validated in the stable operation, so in the stable branch of the characteristic curve. Regarding the turbulence model, since very large turbulent structure were expected, we decided to adopt a hybrid branchless model, so the SAS SST, in order to in deep evaluate the development of the large size structure, but with modeling the smaller one. So guaranteeing a high accuracy in the evaluation of the fluid field, but without an excessive computational cost like in less analysis. So the first thing we've done was a comparison of the fluid field, of an investigation of the fluid field for three different operating conditions. So the first one named as OP1 in the stable portion of the characteristic curve, so safe partial load. The second one in correspondence of the runaway, and the third one in the turbine break area. So here you have reported the velocity streamline evaluated at the runner and guide vanes midspan section. So relative streamline in the runner and absolute in the guide vanes. And as you can see, at partial load, the flow is quite homogeneous. It is well aligned with the blades. Only minor perturbations are present at the midsection of the channels, mainly due to the onset of secondary flow. So flow going from the hub to the shroud because of the low inertia of the fluid associated with the partial load condition. Things change when moving to the runaway. So you can see now that the flow is quite perturbated with the onset of small and large turbulent structure. And the most interesting things to notice is that the blades are affected by the presence of these large interblade vortexes. So there is one there, also one there, and another there. And we will see that this specific feature really affects the machine hydrodynamics. So things really change when moving to the turbine brake area. So here we are in the in an operating region where there's the full development of the machine unsteadiness. And as you can see here, the flow is extremely perturbated. It's no more aligned with the blades, both in the runner but also in the guide vanes with the onset of very large recirculations, and also the presence of very large interblade vortexes. You can see here that are completely choking the channels. It is also interesting to notice that in front of the choked channels, also here, you can see that the water is pushed back into the guide vanes. So the rotor-stator interaction modified the flow distribution also in the guide vanes. And in order to better appreciate the structure of these interblade vortexes, here I reported to you the velocity field evaluated at the normalized mid-span section of the runner and at the 15% span, so close to the hub. And you can clearly see that there is flow going back from the outlet section of the runner into the channels, generating here the secondary, these large vortexes. I have reported this picture in two different span-wise sections in order to show you the three-dimensional nature of such a phenomena. So it's slightly visible in the mid-span section, and it's very clear in the 15% span, so close to the hub. And to further demonstrate and to show you the evolution in the space of this turbulent structure, here I've reported a schematization of those specific turbulent feature. So here you have reported the three-dimensional view of the interblade vortexes in the runaway condition. So you can clearly see that there is a blockage effect on the flow. And here you have the schematization. So the flow, it's actually going backward from the outlet section. It spins with the runner, dragged by the runner rotation, then goes into the channels toward the shroud, and then exits close to the runner shroud sections. So this is a very dissipative motion, so there's a lot of energy consumed because of this. And what is really interesting to notice is that what's the effect of these vortexes? Actually, the main effect of the development of this large structure is an imbalance in the discharge distribution in the runner, leading to the onset of very sharp force pulsations starting from around 15% of the best efficiency discharge. So here you have reported the trend of the radial x direction force during the simulation, while here you have the wavelet analysis of the same signal. So as you can see, starting from more or less 15% of the best efficiency discharge, we have the onset of this very high amplitude structured instability with a specific frequency, in this case is around 17% of the best efficiency discharge. And this phenomena, this behavior, it's linked to the development and the consolidation of the rotating stall. This is actually a quite common feature of pump turbines operating in the turbine brake area. So you can also appreciate the rise in the magnitude of the forces, so in a real case of the vibrations, by taking a look to the amplitude difference in the turbine brake area and as partial load. So there is like a 10 factor in the radial forces. So in order to confirm these results and to investigate if those was only related to this specific geometry, we decided to extend this analysis by simulating another pump turbine. So this is the pump turbine of the Turbomachinery and Energy System Laboratory of the University of Padua. It's a quite different configuration because this is actually the second stage of a double stage pump turbine without spiral case, and so instead of a spiral case there is a bladed return channel. And as another difference, you do not have an elbow type draft tube, but rather a straight type with this pipe inside, which is for the axis of for the shaft of the machine. Also in this case, the runner, it's a quite a common runner with the straight blades. And regarding the model, just a few words regarding the mesh. So the same model as in the previous case was adopted, so same strategy. The only different things is that here we have adopted only structured meshes, and also we have included the front leakage system. So in order to consider also the leakage flow. Passing straight to the results, here you have reported, as in the previous case, the trend of the radial forces acting on the runner, so x direction, together with the time frequency characterization. And you can clearly see that we have a very close behavior with the onset of a structured high amplitude perturbation starting also in this case from 15% more or less of the best efficiency discharge. To better appreciate the common feature between the two runners, here you have reported the fluid field evaluated also in this case in the turbine brake area. So you can see that there is still the presence of very large interblade vortexes. And taking a look to the comparison between the Model A and Model B runner, we can see that the flow is actually characterized by a common behavior. So in the runner Model A, we have the presence of these large vortexes. At the same time, we have a very similar behavior in runner Model B. One difference is that in this case, you can see that the Model B runner is characterized by the presence of a single vortex, very, very large vortex, while in the runner Model A, you have the presence of more vortexes affecting the flow. Also in the guide vanes, we have a very close behavior with the rotor-stator interaction causing the backflows of the discharge. And finally, to really show you the common feature, I reported here the results of the wavelet analysis performed on the torque acting on a single runner blades. And you can clearly see that the spectrum, it's quite similar between the two simulated machines. So starting from 15% of the best efficiency discharge, we have the onset of these really high amplitude perturbations. And it is also quite interesting to notice that the frequency is also almost the same, more or less. So around 17% of the rotational speed of the runner. And this is due to the presence of the rotating stall affecting the runner rotating with the subsynchronous speed of the runner speed. So what's the results of this first analysis? Of course, this low variation of the characteristic curve influenced the pressure, torque, pulsation of the machine, and the development of the flow unsteadiness, the reason has to be found in the development of the rotating stall. So the rotating stall dominates the fluid dynamics of the machine when operating below runaway, so in the turbine brake area. Later on, after a literature study, we have found that some authors investigated the adoption of the blade's lean angle for improving the efficiency in turbine and pump mode, and also to enlarge the operative ranges. Nevertheless, there were at time sufficient studies in deep investigating the relation between the lean angle and the flow unsteadiness. So we decided to propose a comparative analysis by extending the previous simulation to other 4 runner configurations. So we modified the runner by changing the lean angle, and we simulated 2 runners. Oh, sorry. 2 runners with the linear lean angle, 1 positive and 1 negative, and other 2 with the curved lean angle, so forward and backward. For those of them not confident with this topic, lean angle is a very common feature adopted in pump in order to suppress secondary flows. So this allows you to modify the pressure distribution at the runner impeller outlet section, and so to guarantee better distribution of the flow streamline in this section. And usually a positive lean angle is defined when the profile of the blade at the shroud section is rotated against the rotational direction of the machine. So as first results, we can see that this is the results of the characteristic curves evaluated for the 5 different geometries. We can see that none of them is able to fully suppress the S-shaped characteristic. So here we reported in gray the characteristic curve directly evaluated from the numerical signals, while with the solid black line you have the mean trend of the characteristic curve. However, we can see that there are some differences between the geometries. So first of all, we can take a look to the dispersion band of the curves. So the amplitude, the width of this dispersion band is a tool for measure the pressure pulsation at the inlet section of the machine, so the water head. And secondly, we can have a look to the overlap region of the characteristic curve, so the width of the S portion of the curve. And we can see that the runner characterized by the linear positive angle presents reduced amplitude of the S portion. Later on, moving to the analysis of the runner blade torque. So this is the same as in the previous case. So this is the wavelet analysis performed on a single runner blade. We can see that this specific model do not show the presence of the previous mentioned low frequency instability. So actually we can see that there is still a very small amplitude structured phenomena. However, in comparison with the other geometries, we can appreciate that this specific condition is characterized by a reduced influence to the development of the rotating stall. To better appreciate the aspect, I reported here the trend of the torque acting of all the runner blades. So here we have the blades number, so 1 to 7, while here we have the discharge, so this is actually time. You can see that starting from 12–15% of the best efficiency discharge, the torque on the blades is characterized by the onset of this structured perturbation. Actually, you can evaluate the rotational speed of the rotating stall by considering the slope of these curves. And what is interesting to notice is that the runner with the linear negative lean angle do manifest the presence of structural instability, but the amplitude is quite lower compared to the other runners. A further demonstration of the reduced sensitivity to this phenomena, here we have reported the comparison between the radial force for the regional runner and the improved one. You can see that there is still structured unsteadiness at partial load, in the turbine brake area. Nevertheless, the amplitude is extremely lower compared to the original runner. Now, to see how the development of backflows and rotating stall affects the force distribution in the runner, here I reported the trend of the static pressure and the streamline evaluated at the 20% spans of the 0-degree runner, so the original runner, and later of the improved one. As you can see, as in the first simulated machines, we have these large vortexes caused by the backflow. So the flow is going back from the outlet. It is then dragged into the channels and creates these vortexes choking the channel. What is interesting to notice is that in correspondence of the choked channel, we have the rise in the static pressure in the guide vanes and also in the runner inlet section. On the contrary, this is the runner with the negative lean angle. We can see that we still have backflows affecting the channels. It's visible in the pressure field, but also in the velocity streamline. Nevertheless, you can see that the distribution of the pressure in the guide vane is way more homogeneous. So how this perturbation of the pressure affect the radial force distribution? So here we have reported the comparison between the pressure field for the original runner and the negative one. You can see that in correspondence of the choked channel, we have here the rise in the static pressure. And this is the same results as in the previous slides. In this specific time instant, it is clear to understand why there is a downforce, because the pressure distribution in the top section of the runner is higher compared to the lower one, and that's why in this specific time instant you have a negative force pushing back, pushing down the runner. On the contrary, you can see that this specific configuration is still affected by a very perturbated fluid flow, but with a quite homogeneous pressure distribution in the guide vanes. So, what's the conclusion? Flow unsteadiness in pump turbines is still playing, still represents a key challenge in the development of new pumped hydro storage facilities and in the development of technologies for allowing for the distribution and the widespread of renewable energy sources. Nevertheless, these results demonstrate that we still have margin to improve not the efficiency, but to improve the operative condition of pump turbines. So there's margin to propose new design guidelines and new hydraulic modification in order to extend the operative ranges of pump turbine and to increase the flexibility. And with this, I would like to thank you for your attention.
Thank you very much, Giacomo. Very nice presentation, very interesting. We have time for a little questions, either from the audience here or from online, if there is any. Or we can keep the discussion for later with all, let's say, panelists together. We keep it for later then. Thank you. Okay, so the next presenter will be Aldo Leonardo Alerci. He is from École Polytechnique Fédérale de Lausanne, the technology platform for hydraulic machine. I'm actually co-supervising his PhD thesis. He's also at the very end of his PhD, will conclude in the next 6 months. And today he will present the modeling, optimization, experimental analysis of transient-induced fatigue in hydraulic machine, providing power system flexibility. Leo, the floor is yours.
Yeah. Thank you, Elena. So good morning, everyone. As Elena already introduced, I'm a PhD student working at the technology platform for hydraulic machines at the EPFL in Switzerland. And today I'm going to present a work which is based essentially on the assessment from the point of view experimental and also from an analytical point of view of the transient-induced fatigue on specific case of hydraulic machines, including also an optimization framework. So in my presentation, I will before introduce the context and the main motivation of the work, and then I will go through the concept of fatigue before from a general point of view, and then apply to hydraulic machines. I will then dive into the methodology, which is divided between an analytical modeling and the experimental setup that allowed us to both evaluate and optimize the impact of fatigue of two specific hydraulic machines, in this case, Pelton turbines and centrifugal pump, and then I will conclude with the main outcomes of the work. All the work is framed within the HydroLeap project, which is a research project funded by the Swiss Federal Office of Energy. So regarding the context, as my colleagues Ludwig and Giacomo already introduced pretty well, I will not insist on it, but basically we are seeing in the next decades as forecasted increase in the electricity demand, and in the specific case of the European power system, we will see that in the next decades, in very important fraction of this demand will be, at least it is planned to be covered from renewable sources, and most of them being intermittent, are basically introducing a stochastic production in the power system. And in parallel to this, so in parallel to this ambitious, let's say, energy targets, this research also relies on another issue that the electricity industry is currently facing, namely what is linked to the structure of the electricity industry, which is nowadays regulated around markets. And one of the consequences from the coupling within these two elements is that TSO nowadays are required to adjust their generating schedule, introducing the so-called redispatch measures. And hydropower plants are, due to their nature, very, very flexible nature, are very well suited to provide this flexibility to the power grid. But this has a cost, and the cost is that the hydropower plants are undergoing more and more frequently transient operating condition as the startups or the shutdown in their operation. So, doing this in this concept, there are basically three main research questions that arise in the particular case of pumped storage power plant, namely how are the pumped storage power plant equipped with ternary groups affected by the impact of this operation, and if this can be assessed, how we can do it, and finally also if there are room of improvement to try to optimize the operation, still fulfilling the requirement of the power system. And all these three research questions, we will investigate them related to the real demonstrator, which is located in the Western Switzerland. We will see later on. So before diving into the methodology, we'll introduce very quickly what's fatigue and how this applies. So basically, fatigue is the detrimental phenomena that happens when a solid structure is loaded with cyclic loading. And it is a phenomenon which is typically evaluated experimentally, since we have to bring the materials to failure. So what happens here? Here you have typically what is called the Wöhler curve, so a curve which is plotting the relation between the stress amplitude of our cyclic loading against the load cycles that bring our structure to failure. And typically, to evaluate the damage in terms of lifetime reduction for our structure, we use a damage rate, which is basically considering that each cycle of our loading is providing a single contribution, and that each single contribution can be summed up to end up with a damage rate. And when this rate reaches the value of 1, at least statistically, our structure will fail. And in parallel to this, which is the most well-known approach in terms of fatigue, we also have another approach which takes into account more specifically the physics of the problem, and namely the investigation of the physics of the propagation of cracks inside solid bodies. So what you can see here on the right is a typical plot of the crack propagation trend. So we're showing the crack growth rate with A, the crack size, the size of our crack, and N, the number of cycle of our cyclic loading. And basically we are showing it against delta K, so stress intensity factor, which is depending on the amplitude of our stresses and the current crack size. This is important to know it later on. So we can split this propagation, this trend, in three main regions. And what we see is that for the most common model that we have, so the Paris law, is basically describing the second stage, because the structure spends the vast majority of its lifetime in this second stage, so not in the incipients and when we go to failure. But for us, it's also interesting to investigate another model. So in this case, the Walker law, since we are also interested in the stress ratio. So taking into account not only the stress amplitudes, but also the average value of the stresses around which our cyclic loading is happening. So basically when the cyclic loading is not happening around the value of zero stress. Regarding hydraulic machines, so I will cover a bit the phenomena that are happening. So in terms of centrifugal pump, I will go very quickly. So our colleagues already introduced the most common phenomena for centrifugal pumps. So basically rotor-stator interaction and rotating stall, but we can also have phenomena as recirculation, separation, or cavitation that are responsible to induce important dynamic loads on the structure. And also from the point of view of the mechanical imbalances, we can have some important loading on it. Here you can see a schematic of the rotor-stator interaction, whereas here we can see two different examples of cracks of failure for reaction machines. I'm not sure, I think this is a pump turbine, whereas this is a French turbine, but I mean the principle stays the same, with the hotspot location in terms of stresses that are basically the intersection between the blade and the crown. Regarding Pelton turbines, the situation is pretty different. So the main excitation for the dynamic loads is the water jet that impinges on the buckets. And here we have an important stressor that develops at the bucket roots, since we are exciting the bending mode of the bucket. As we can see here, our main interest point at the bucket root. And we can also have potentially dynamic amplification due to the interaction with the modal behavior. So, which is interesting is also to investigate the modal behavior of the runner to try to catch the possibility of this excitation. So the aim of the project is to investigate experimentally and assess how this impact is important for these hydraulic machines. But we noticed that given the more simple nature in terms of geometry and excitation for Pelton turbine, this led us to the idea to trying to develop an analytical model, not only assessing experimentally for the Pelton turbines, but also to try to forecast the stresses and therefore also the impact on the fatigue lifetime. So the idea was to reduce the complexity of the system and try to build this analytical model to both evaluate, so predict the bucket dynamic, and also trying to build an optimization framework to be later on applicable on real measurements. So that's what we did. And basically the idea was to isolate from a Pelton turbine, isolate in the system of interest, so in our case the bucket, and trying to express the excitation on it. So basically the centrifugal force which is acting radially on the runner and the jet force which is acting tangentially. And to reduce this structure with a simple one, in this case a cantilever beam, which is basically the schematic of our bucket. And the idea was trying to explicit the excitation terms of centrifugal force and the jet force via the Fourier analysis to be able to extract the dynamic response of the displacement of our structure. So basically having the analytical expression of the displacement. And with this, so the steps from the displacement to the stress at the intersection here, so at the bucket root, is pretty straightforward. And we notice afterwards, when we had also stress measurement, that we have a quite good prediction for high rotating speed, whereas for slow rotation, the prediction was quite bad in reason of the inherent nature of Fourier analysis, which is based on steady state and periodic nature. And when we have slow rotation, of course, we have the damping of the bucket, which is very important. So we have transient effects that we didn't take into account with our Fourier analysis. So the step from the forecast of the stresses to the fatigue is could be pretty straightforward, but we noticed that with the two methodologies I showed you before, we have few kind of problems. So these methodologies that I show you are relying on counting cycle algorithms to counting the cycle of the loading, and also present threshold in stress amplitude to calculate the fatigue impact, and are described by power laws. And when dealing with stress estimation, not measurement, even with small errors, we can end up with a potential order of magnitude in the damage. So the idea was to try to have a representation of our damage, but trying to be not too wrong, to have a first idea of how the damage can evolve. So what we do is that we take an alternative approach, basically calculating the energy of the signal of every operating condition that we calculate. And this is essentially the strain energy which is stored in the oscillation of the bucket. So we used this quantity to evaluate our damage, and we calculated in the entire operating range of our Pelton turbine at steady state conditions. So with our operating range discretized regarding rotating speed, omega, and the discharge. So for the Pelton turbine, the opening rate of the injectors. And in parallel to this, so not only to try to give an estimation of the fatigue, but we also try to build up an optimization framework. And for Pelton turbines internally groups, one operation which is pretty relevant is the back-to-back startup. So basically when with your generating units, you're putting in rotation the pumping units to bring it to synchronization. And it is pretty interesting from the point of view of dynamic loads, because we have high mechanical torque. We are not putting in movement only the turbine, but also all the multi-stage pump. And we also have an influence of the pump rated power. So this depends on both sides. So the aim of this step was trying to minimize the damage which is accumulated during the acceleration on the Pelton turbine, making the hypothesis that we can get the damage from the steady state damage that we calculated before. So the idea of our optimization problem was to define an objective function, which is basically the sum of the damage for each dt, of each time step of our acceleration. And the constraints basically are including a consistent behavior of the hydropower plant, so with our motion law and an upper bound on the injector opening rate. So we cannot open our injector in 1 second, for example. And the final, initial and final state within also the synchronization phase, the end of the acceleration. And so we ended up with a non-convex problem in reason of the interaction between our operating condition with the resonance modes of the bucket. And the problem with this that you cannot solve with simple gradient descent-based algorithm. So we need to relax our problem and to make it convex, and we did it with semi-definite relaxation. So we'll not plot all the solution that we had, but basically the optimal global solution was strongly dependent on this factor, so on the upper bound that we put on the main reactivity of our injector opening rate. Now we have a model that we can handle with convex and non-convex problems in terms of an optimization. So it's now the moment to go to the experimental assessment and try also in this case to both evaluate and optimize the operation of our Pelton turbine. So in our lab we can test Pelton turbine in a dedicated test rig, which is conforming to the IEC standard that can reach until 400 meters of head. And the reduced scale model that we tested is basically the same geometry according to the pumped storage power plant that I told you before. So it is a 240 megawatt pumped storage power plant with a gross head of about between 800 and 900 meters. And we have 4 units. Each one with a 5-stage centrifugal pump that you can see here in the photo and here in the schematic. And each unit has a generating unit, which is represented by 2 Pelton runner that you can see here with the 2 sets of the distributors. With a reduced scale ratio of about 5 times, this translates with a net head of about 168 meter. And we implemented our reduced scale model with strain gauges on board the runner. So we used both resistive strain gauges at the bucket root that you can see here in the photo here in the 3D model, and also piezoresistive strain gauges on the rear surface of the bucket. You can recognize it here a bit and here indicated by the red letters. Of course, so in the end, we ended up with 12 sensors, but here what I show you is concerning only one resistive strain gauges in reason of the location, which is the hotspot, as we saw before. In terms of similarity, during our test, we try to fulfill kinematic similarity, which is represented by speed factor and discharge factor, and also the fluid similarity, which is a strong requirement when testing Pelton turbines in reason of the multi-phase flow that develops in the casing. And trying to keep those three terms equal between a reduced scale model and the real scale prototype allowed us to fulfill the velocity triangle similarity and the hydraulic condition. Moreover, when talking about transient operation, those similarities has also an impact on the time scale, so in the length of our sequence that we are testing, which is ended up with a ratio between the time between the prototype and the model scale, which is a function of the geometrical scale ratio. We also try to extract a scaling law for the stresses, so considering the two sources of dynamic loads, in this case the force of the jet and the centrifugal force, we ended up with two different scales. And this could be a problem because to try having the stresses for the prototype scale signal, we had to basically split the signal that we had on the reduced scale model and then rebuild it up according to the two different scales. So now it's the time to pass to the evaluation of the fatigue phenomena, and in this case I will focus on the crack propagation approach in reason of the time that we have for the presentation. So basically, when we have rebuilt our stress measurements, we apply the counting cycle algorithm, which provides us with the number of cycles in stresses with a specific stress amplitude and a specific stress average value. And integrating the Walker law that I showed you before allowed us to express the crack length after a specific time step, dt, as a function of the crack length of the same crack, but before the time step dt, and a summing term, which is basically a function of the stress amplitudes and different parameter of the material. So basically the output of our counting algorithm. And here we don't have an explicit dependence on the crack length, but the crack length here is affecting basically the terms that are inside here, because depending on the stress intensity factor, also including the crack length, we can or cannot cross a certain threshold in the terms of propagation. And this means that for each kind of crack length that we have currently, we will have a different damage. And the damage can be represented by this term that we can assume as the crack advancement for each time step and can be basically plotted. So here we can see, for example, this term, which is plotted for the current crack length of 1.7 millimeters. So of course we have to put some hypothesis on the current crack length that we have in our solids, so where we have our strain gauges transposed to the prototype scale, and we plotted here as a function of the rotating speed and on the injector. And for example, we have another case, so exactly the same situation, but with a crack length of 2.3 millimeter. So the idea was, okay, we have plotted our damage yield chart, and now we try, as before, to implement an optimization algorithm, always considering back-to-back startup of the multi-stage pump performed with the Pelton turbine, with our initial condition here, so the standstill point, the target point for the Pelton turbine, which is dictated by the rated power of our multi-stage pump to put in movement, and also for the BIP, the best efficiency point. So we can see the position, of course, of the condition are pretty the same, but the damage that we have for this condition is not the same. So the idea is to put the same principle of optimization algorithm as before, but this time the objective function that we are trying to minimize is the crack length that we have in the end of the acceleration. The constraints are the same in terms of the hydropower plant dynamics and in terms of the initial and final state, so standstill and synchronization phase at the end. In this case, we have a almost convex problem on our propagation region, so no need of different kind of relaxation, and we can handle this problem with gradient descent based solver. In this case, we need an initialization, so an initial solution, and we use for it the back-to-back startup, which is currently performed on the hydropower plant, also to be able to compare our optimal solution. And what we did, so we could have this optimal solution for each different case, each different scenario, depending on the crack length, and try to implement these sequences on our test rig. So we performed our transient experimental campaign, and we collected the signal from it. And we ended up with these results. So basically, for different cases of crack length, we had an optimal solution, which is compared with the baseline solution. And we see that for the vast majority of the cases, especially when crossed a certain threshold in the crack length, we are able to optimize, so to reduce the length of our crack. So for what we did an hypothesis in the beginning from different kind of percentage, but we see that the algorithm is pretty valid. So I call it semi-validation because, of course, we are not able to measure the crack that we are making the hypothesis is existing, but at least with the same theory applied on the steady state regime and then applied on the transient signal that we could collect from our transient operating condition, this will be the theoretical results of our crack evolving all around. So that's nice, but for the Pelton turbine, so what about the centrifugal pumps? Because we are optimizing for the Pelton turbines, but we don't know what happens for the centrifugal pumps. So this experimental assessment is still ongoing at the laboratory. So we had our experimental campaign, but the post-processing of the data is still ongoing. We didn't plan an optimization framework. So basically, we are just evaluating what happens on the centrifugal pumps when we optimize regarding the Pelton turbines. So in this case, we are also performing experimental campaign with the reduced scale model of the multi-stage pump, which is built up according to the geometry of the real pump storage power plant. And we have an instrumentation also on board the impeller. So in this case, we instrumented two blades, one in the pressure side and the other one in the suction side, to have the same channel. Basically, we have blade number 2, blade number 1, same here. And we placed our strain gauges in the critical location in terms of mechanical stresses, so at the intersection between the blades and the crown. And the idea is to, before everything, try to evaluate the impact of fatigue if we implement the same sequences that we consider optimal for our Pelton turbine, and also, for example, to detect rotor-stator interactions. So we also have pressure fluctuation in the stator in the casing, and basically we only instrumented the last stage, so we didn't instrument all the run. But still, as I say, this is an ongoing process. So to conclude, what are the main takeaways from this study? So we had an overview of the main cause of fatigue that are impacting on hydraulic machines, in this case only on Pelton turbines and of centrifugal pumps. And we saw that the structural damage can for sure be experimental assessed on reduced scale model, but in the case of Pelton turbine also can be forecasted analytically. And in this case, for Pelton turbines, we managed to have an enhancement of the operation through an optimization framework in both cases. So both cases of our analytical model that we use to forecast, and also from the point of view of the experimental assessment. And as I said, so this optimal operation can be semi-validated, of course, not validated because we don't have the monitoring of the crack. However, it is crucial, as I said, that this optimization will not impact in a too negative way the structure of the pumping units. And also that all this analysis that I presented to you is based on very well-known structural hotspot. So we are optimizing, for example, in the case of the Pelton turbine regarding the bucket root. But the hydraulic machines and also the installation can suffer unexpected behavior impacting other kind of elements. So for example, in the power plants that I showed you, we had recently cracks detected, for example, in the intersection between the shaft and the Pelton runner, or also in the casing of the pump. So you can have cracks happen basically wherever you want. So you can optimize for a single pump, but you cannot necessarily optimize for all the structures that are involved in the power plant. So with this, I finish my presentation. I thank you very much for your attention, and I open for your questions.
Thank you very much. Very interesting. Our questions. We have maybe 3-4 minutes if anybody has a question for Leonardo or for one of the previous speaker. Online?
No.
Oh, yeah, that's perfect. Yeah. Okay, so the question. Could you please list the decision variables of the optimization problem by which you optimize the back-to-back startups so that crack advancement in bell-to-bucket route is minimized?
Yes. So the decision variables are the two variables that regulate the operating condition of our Pelton turbine. So basically the opening rate of the injector, so the discharge that we have, and the rotating speed that we have during the acceleration. For this case, when we try to minimize the crack length, we also had another parameter that are the duration of the sequence, but this we didn't use it as a decision variables because from the point of view of crack propagation, we have a large zone that I showed you before. Maybe we can close. We have very important regions where basically the propagation is 0. So we cannot really leave our duration of the sequence as a variable because essentially here we can stay for theoretically at least for 1 hour without propagating anything. So we could not leave this as a variable and we set it for different cases ourselves. So it is not entering as a decision variables, but it could also be considered for this. But in our case was basically rotating speed and the injector opening.
Thank you. Good. I propose so now to do the break. We will have come back to the agenda. So we are perfectly on time. We will have about 10 minutes coffee break, and we will start back so at 10:45. Thank you. Thanks to all speakers who presented already so far.